So the plan for today is to talk about partial derivatives, and then also if you want to go over any of some practice exam stuff, we certainly can do that as well. But before we do that, I just want to start with one quick thing. Last time we were talking about open and closed, and there was some discussion about it, and I feel like people might not have a great idea of exactly what's going on. So there is this definition in your book, which is kind of what I've said, just very explicitly pointed out. So I'm going to read it to you, and then we're going to talk about it for just a minute. So definition. This is section 14.1. A point in a region or set in the XY plane is called an interior point if it is the center of a disk of positive radius that lies entirely in R. So that's like what I was saying last time, is basically your point I didn't use the word interior point, but an interior point is a point that if it's in the set, you can draw a circle around it and that circle is still in the set. Then we also have a boundary point of R if every disk centered at the point contains points that lie outside of the set. So that was like when we had the edge of the circle. If we drew a point there and drew a circle around it, you always got points that were outside of the set as well. And then going on further, yeah, so boundary point, yes, okay. So then the interior points of a region make up the interior. Okay, that seems kind of like, of course. And the region's boundary points make up its boundary. Okay. And then finally, a region is open if it consists entirely of interior points, meaning every point needs to meet that criteria where if you pick a point in it, a circle around it is also contained in the set. Whereas a region is closed if it contains all of its boundary points. So I just wanted to kind of give you the more formal definition of what we were talking about on Tuesday. Yes.
I understand this definition.
Sure.
But then when they give this equation, I have no idea how to match that.
Sure thing. So like, what kind of equation, for example? Sure, okay, that's fair enough. So let me give you a couple quick examples and then we'll move along. So let's say we had, I'm gonna give you two different functions. So, and both of these are gonna be not terrible, I think. Let's say the square root of 64 minus x squared minus y squared. And we specifically just want to talk about the domain for a second. So here the domain, we need that stuff in the square root to be greater than or equal to 0, which is going to end up translating to x squared plus y squared being less than or equal to 64. We know that x squared plus y squared equal to 64. Oops. Is a circle of radius 8. Center is the origin. So we try and draw our domain. Well, first of all, we're going to include the boundary here, right? Because we want x squared plus y squared to be less than or equal to 64. So for my circle of radius 8, I'm definitely including the boundary. There's the 0.08. There's the 0.80. So just from the language I'm using, you might think it's probably going to be closed because I'm already talking about how our domain is including the boundary. And that's not wrong to think that, right? We're definitely on the right track if we're thinking that way. So, and then we should label if we want the inside to the outside. So I'm going to pick a point like the origin, and I see that the origin definitely satisfies the inequality. Right, 0 squared plus 0 squared is less than or equal to 64. So I definitely want everything inside of this circle, including the boundary. So two things. First, is this open or closed? Well, so we think it's closed. Is it closed? Yeah, because every boundary point, so like there's a boundary point right there. Well, first of all, is that a boundary point? If I draw a circle around it, some of the circle is outside of the domain. So definitely that's a boundary point. Any point on the thing I have called the boundary is a boundary point. And specifically, this domain includes all of its boundary points. So this set, with the domain being the set containing all points inside and on the circle, the point of all x, instead of all xy, such that x squared plus y squared is less than or equal to 64. That is definitely closed because it contains, welcome, thank you, all of its boundary points. The other question we might as well address while we're here is it bounded or unbounded? Well, if we go back to the book for a second, very specific about what they mean. So when I think about being bounded, I think, well, X and Y can only be so big or so negative, that there's a limit to how big either one can get. Whereas unbounded typically means one of X or Y can either get infinitely large or negatively infinitely large. The way they write this in the book, a region is bounded if it lies inside a disk of fixed radius. Okay, that seems sensible. If my region can be drawn inside some finite radius disk, then it seems like it should be bounded because you're containing it within something. Whereas a region is unbounded. Okay, it's gonna feel, that's always great when they do this. A region is unbounded if it is not bounded. Okay, I mean, right. So if you can't draw a disk around it, it's going to be unbounded. Or as I like to think, if X and Y can get, or if X or Y can get really, really large or really, really negatively large, it's unbounded. So this is definitely bounded. Let's look at two more examples. The next one's going to be almost the same. Because instead of the square root of 64 minus x squared minus y squared, we're going to look at f of xy being the natural log of 64 minus x squared minus y squared. And the only difference here is that now my domain is all that stuff has to be greater than 0, which is going to end up meaning that x squared plus y squared is strictly less than 64. So our region is going to look like the same circle of radius 8, except now we are not including the boundary points. So now we're inside. We can write the domain as a set of all x comma y, such that x squared plus y squared is less than 64. It's still definitely bounded because, again, just like before, you can contain this region in a circle of some finite radius or disk. Right? I would say circle, but fine, disk. And then secondly, is it open or closed? Well, it's definitely open, right? It includes all of its interior points, right? Every point that's an interior point, meaning every point in there, you can draw a little circle around it and it's still in there. So it's definitely open. It's also definitely not closed, right? It definitely does not contain its boundary points. So I suppose I should be specific and say it's open and not closed. I think your professor is kind of big on that idea. So I would certainly, here I should say it's closed and not open. Right, it's not open because to be open, all of the points in the set have to be interior points. And that point right there is definitely not an interior point. So boundary points aren't interior points. Interior points aren't boundary points. They are definitely distinct from each other. But sure. And then finally, the one that always jams people up is something that seems relatively innocuous, like f of xy equal to, sure, let's say it's x to the 4th plus y squared minus 8. We'll talk about the range here too, because why not? Domain. I got no domain issues, right? There's no roots, there's no logs, there's no fractions. So my domain is not the entire real number line, right? It's not this. The domain is all of the xy plane. Or you can say it's the set of all xy such that x is real, y is real. Or you could say it's the set R2, D2. Open or closed? Both. So, right, the set of everything, welcome, is always going to be both. And we can look back at our definition. So if I look at the entire plane, every point's an interior point. No matter what point I pick in the plane, I can always draw a little circle around it that's still in the plane. So definitely open, because the set contains, or I should say, the set is entirely made up of interior points. Okay. It's also closed because it contains all its boundary points. Oh, there aren't any boundary points. It still contains all of them. So it contains all of its non-existent boundary points. Definitely unbounded, right? Like no argument there. And then finally, just to say what the range is, the range here would be everything from -8 inclusive to positive infinity. Right, this can be as small as -8 because x can be 0 and y can be 0, but that's as small as it can be, and it can be as large as infinity. Usually we don't ask about the open or closedness of the range, but I will just state that the range is closed and not open. It's definitely closed because it contains all its boundary points. That one right there. It's definitely not open because not every point is an interior point. That one right there is a problem. Yeah. Ah, good question. Yeah, fair, good question. So if, for example, if my function f of x, y was, so to get everything flipped, you essentially change the signs of everything. So it'd be more like the square root of, instead of 64 minus x squared minus y squared, it's going to be x squared plus y squared minus 64. So then we'd have x squared plus y squared greater than or equal to 64. We'd have the same circle. And then everything, I really hate drawing this, everything outside the circle, it always just feels like it doesn't look good. So there's our domain. Okay, so first of all, our domain, set containing x comma y, such that x squared plus y squared greater than or equal to 64. The restrictions are just square root and natural log. Also, don't forget possible division by 0. So if you have fractions, that's also something you have to look out for. So our function, is our domain bounded with a thumbs up or unbounded with a thumbs down? 1000% unbounded, yes, for sure. And again, the way I would encourage you to think about it is just that x can get really, really large as you want. Y can get really, one of them can get infinitely large without bound. Like, did you look like you had a question?
No, it
Okay.
just confuses me because for being closed when it's an infinite thing, the boundaries are somehow considered to be like negative infinity and infinity.
Well, so what I would say is there aren't boundaries when it's the whole entire set.
But the not boundaries count for whether or not it's closed.
Well, it's not that they count, it's that, so again, to be closed, a set has to include its boundary. But the entire real plane doesn't have a boundary. So if I don't have a thing and I have to include the thing that I don't have, well, it's automatically included because there isn't one to include. I know it sounds, you're right. It sounds like some, no. This is where people start to really kind of like hate math because they're like speaking gibberish. Right, it's right, exactly. It's kind of like, so sometimes here's something that is maybe somewhat analogous, but not perfect. We talk about in statistics or combinatorics how to count things. how to choose groups of people. So if I said, there was this group of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people, and I want to know how many ways can I choose one of you? Well, there's 10 ways. I can choose you or you or you or you, right? How many ways can I choose none of you? One way. I don't choose any of you. It's the same kind of idea where there's still a thing, even though I'm not actually having to get anything from that. But yeah, it's kind of annoying. So when you look at the whole thing, if it's unbounded, right? No, not unbounded. If there isn't a boundary, which is different than being unbounded, right? So I will point out this set here, all the stuff out here, including the circle, because the circle is definitely included. This set is definitely unbounded and has a boundary. This is the boundary. So this set is definitely closed and not open. It's closed because we include every boundary point that exists. All these boundary points here are included. Great. But what if I had everything? Well, all the non-existent boundary points would still be included. The restrictions is how to format restrictions for the fraction. Sure, we can talk about that. And then, sorry, just to go along with the other one. So to look at the other function, if it were f of xy equal to the natural log of x squared plus y squared minus 64, then we'd be looking at something more like this. Everything outside of there. And then the set would also be unbounded. And it would be open and not closed. Open because every point is an interior point, or every point you can draw a little circle around and it's still in there. And not closed because we don't include all the boundary points. There are boundary points right here that are not getting included. Yeah. It is the outside of the circle and the boundary of the circle. So it's all of this boundary is part of what's included, which is why I've drawn it solidly and not dashed, and everything out here. That's my domain, all this, including that, right? This point here, all this, right? All this. So the entire circle is part of the domain. Whereas in this one here, this circle here is not part of the domain. I do not want any of the points on the circle. So it's all the stuff out here. So in this one, if I pick this point right on the circle, it's definitely a boundary point, right? If I draw a little circle around it, some of that circle is not in the set that I'm looking at. One sec. Whereas on this one, and that point's included, right? The point 0, 8 definitely is in the domain. 8 squared or 0 squared plus 8 squared minus 64 is 0, and I can take the square root of 0, no problem. Whereas here, the point 0.8 is not in the domain, right? 0 squared plus 8 squared minus 64 is 0, and the natural log of 0 is undefined. So for this one, we're getting that it's closed because we are including every boundary point in the domain. And this one, we're getting that it is open because because every point that we're including is an interior point, or we're not including the boundaries that I really think about it.
Why is the bottom one not both open and closed? Because aren't there not boundary points?
Give me one sec to that. You had a question?
Yeah,
Sorry,
I was wondering if we can just specify if it's whether it's closed or open, or do we have to say closed and not?
I think your teacher, at least I think Tavernetti specifically wants you to specify closed and not open, because there are some sets. Okay, there's two types of sets. There are some sets that are both closed and open. So being closed doesn't necessarily preclude you from being open. Being open doesn't necessarily preclude you from being closed. But I will mention those in just 1 second. So your question was, what was it again?
The last one, why is it not both open and closed?
So to be closed, we have to include all of our boundary points. There are some boundary points right there. They're not included.
Okay.
Right? That's the, right? Yes, because we have boundary points and we do. So I should say, because there are boundary points and we are not including them
So
in our domain.
does any like line drawing that's dashed, those are boundary points?
Yes.
Don't actually count.
Yeah.
So-
Yeah. So essentially, to be closed, if there's a boundary, you have to include it. To be open, if there's a boundary, you have to exclude it. That's kind of the name of the game. So basically, closed or open boils down to, is your inequality a greater than or equal to? Oh, it's going to be closed. Or a not greater than or equal to, right? A strictly greater than. It's probably going to be open. I don't want you to get too caught up with all, like, I know we're talking about this, but we should probably move along because this is not like the highlighted. There might be one question about this on your test, maybe not even one. The last thing I'll say about this, because I know it was asked, is, well, two things. One, once again, all of R2 is both closed and open. And not that you're probably going to run into a function whose domain is the empty set, but also the set containing absolutely nothing is also both closed and open. For the same lame reasons that the entire plane is closed. That entire plane is closed because it contains all its boundary points, which there aren't any of. The empty set is closed because it contains all its boundary points, which there aren't any of. It literally has no points in it. It's also open because every point in it is an interior point. Oh yeah, all the points in it are definitely interior points. Look at them. Look at all those points in there. None of them. They're all interior points because there aren't any of them. I know it feels, again, kind of like we're making shit up. We kind of are making shit up. I mean, right, really, like, math is all made up. People invented. I mean, some people, okay, discovered, invented, whatever. We made it up. And we said, these are the rules. And as a consequence of how we made the rules, some weird things sometimes happen. These are some of the weird things that sometimes happen. One more example, just because someone did ask about it. Let's say we had, how do I want to do this? Sure. Let's say we had f of x, y equal to x squared plus 1 over the square root of y minus 2x. That's a good one. I like this, yeah. So domain. Well, let's see that stuff there, y minus 2x had better be greater than and not equal to 0. So already, before I've written down any pictures, draw anything, I'm already thinking it's probably going to be open because my inequality does not have an equal sign. It's a strict inequality. If I'm going to draw it, I'm going to draw y equal to 2x, and I'm going to draw it dashed because I don't want to include that boundary. Even just saying those words should make you think, oh, it's probably open because I don't want to include the boundary. Now, which side of the boundary is it going to be? Well, let's pick a point on one side. I'm going to pick a point over here, 1, 0. I plug in 1, 0, 1 for x, 0 for y. Oh, that doesn't work. So I don't want all this. I do want all this. My domain, which is the set of all coordinates x comma y, such that I would probably write it as y is bigger than 2x instead of writing it as y minus 2, but it really doesn't matter. My domain is definitely unbounded. I cannot draw a circle around all of that. I should say I can't draw a circle of finite radius. I suppose I could draw an infinite radius circle if that's a thing. And it is definitely open and not closed. It is open because every point in my domain, if I pick a point, I can draw a little circle around it and it's still in the domain. It's not closed because I don't include my boundary points, right? That point right there definitely is a boundary point and it's not included in the domain. Okay, I think we've done it to death. We're going to move on. Happy to talk about it more and drop in at 3 if you have questions. So yeah, out of the way. Let's talk about partial derivatives. So partial derivatives. Now, most of what you want to know about partial derivatives is kind of just how to do it, right? Like how to execute it. But I feel like I at least owe you a tiny bit of explanation as to what it really means. So let's look at one example where I'm going to try and draw a not terrible picture. So f of x y equal to 9 minus x squared minus y squared. I like to think of this as a little mountain or hill where it's a paraboloid opening downward. In fact, why am I trying to draw it in the air when I can draw it on the paper? So yeah, I'm usually more like this. So, oops, okay, that's not quite as parabolish looking as I usually like to draw it, but oh well, it's just life. So here is my downward opening paraboloid. Here's my z-axis, my x-axis, my y-axis. I clearly now I've cut it off, right? Because this would keep going down, 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 down. I just can't draw all of that. So we have an upside down paraboloid. It intersects the XY plane. Or what I should really say is the trace in the XY plane is a circle of radius 3. So let's look at what's happening at the point 1, 2, 4, which is 1 in this direction, 2 in that direction, maybe like there, and 4 in that direction. So at the point 1, 2, 4, which is on a level curve of height 4, meaning if we go up 4 here, this curve is on that height. And I know, I feel like this dashed line here is kind of interfering with this other dashed line. Sorry, that's such as sometimes that happens. It's my backwards one there. But we're interested in what's happening at this point here. Specifically, if I travel from this point in the out towards you X direction. So basically, if I travel this way down the mountain, what's the slope at the point 1, 2, 4? Well, the slope in the X direction at the point 1, 2, 4 is going to be, well, I'm going to find the partial derivative with respect to X. And you can write it this way. You can also write it this way. So F sub X or del F del X. Those are del's, not D's. They're a little curlier. If you draw them as D's, no one's going to care. Probably. Just make it ambiguous. So then my partial derivative with respect to X, well, the derivative of 9 is 0. The derivative of negative X squared is negative 2X. And the derivative of Y squared is 0. Because if I'm moving in the X direction, there's no change in Y. Right? And so this is where it's really important to actually understand what's happening. We are limiting our motion to forwards, backwards, really forwards. Right? We're starting here, we're moving forward towards you in the X direction. Y isn't changing, right? And if something isn't changing, its derivative is 0. So something isn't changing, it's a constant. And its derivative is 0, which speaks to the larger picture of when you do partial differentiation, whatever thing you're not differentiating with respect to, those other variables, we treat them like constants and their derivatives act as such. So specifically here, if I want to plug in the point 1, 2, 4, which I might write this way, or I might write as del F del X evaluated at 1, 2, 4. I'm just going to plug in 1 for X and get negative 2. So what that means is at this point in the moving towards you direction, the slope of the tangent line is negative 2. And then we can ask the same question in the Y direction, which see if I can ruin my picture totally here. If instead I think about the Y direction, yeah, we can make that happen, sure. Oh, it's pretty good. He says before finishing the picture. Getting a little ahead of yourself there, James. It was pretty good. It's less good now, but it's still all right. So at that point there, if I'm moving in the forward Y direction, if I'm moving that way, What's the slope of the tangent line right there? Well, again, I'm just going to find the partial derivative with respect to y. It's going to be very similar. It's going to be negative, or sorry, it's going to be 0 minus 2y. And if I plug in my point, 1, 2, 4, it's going to be -4. So it's a little steeper going that to from left to right at that point than it is going from back to front. But they're both negative, right? We're definitely moving down the hill, right? If I move from this point rightward, I'm definitely going down, 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 down. If I move from this point going outward, I'm going down, 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 down. Questions so far? So partial derivatives are just, you treat the non-variable, the variable you're not taking derivative with respect to, like a constant. I should point out a couple other things about this example before we get going too hard here. We can take second derivatives. So I want to find the second derivative f(x), especially write the function again. So this is a reminder, f of xy is 9 minus x squared minus y squared. f(x) is just the partial derivative with respect to x. I blew it there. I didn't mean to write that. Sorry. Let's try that again. I made a small mistake, which is fine. But the second partial derivative with respect to x is the partial derivative of x with respect to the partial derivative of x. So that's going to be the derivative with respect to x of our -2x, which is just -2. Which speaks to the concavity, right? If the second derivative is negative, it's concave down. At least it's concave down in the x direction. Similarly here, del squared f del y squared is going to be del y of del f del y, which is del y of -2y, which is also -2. And not surprisingly, looking at the picture, it's concave down in both of those directions. And again, you can use this notation or you can use this notation. This second notation is usually less writing, right? Del squared f, right? Del L squared f del x squared is kind of like a lot to write. And then we also have mixed partial fractions, where you take the partial with respect to x and then y, or y and then x. So if I want to find, say, del squared f del x del y, that is del x of del f del y, which is the partial derivative with respect to x of the partial derivative with respect to y, which was -2y. But the derivative with respect to x of -2y is going to be what? Big old 0. Okay, now I want to point something out that is a little lame, but is what it is. If I wanted to write this in the other notation, fyx. So when you write this notation, you do the partial derivative with respect to y first and then x. You read from left to right. This notation, you read from right to left. I do the partial with respect to y first and then x. So these are the same. In the similar way, del squared f del y del x, which is del y of del f del x is del y of -2x, which is also 0, which is f x y. Now here's what most of the time happens. Most of the time, these mixed partials are equal to each other. So most of the time, the mixed partial, the order doesn't matter. But I will tell you, it is a most of the time. It is not an all of the time. There are really funky functions where you can take the partial derivative with respect to one way, the mixed partials one way, and the mixed partials the other way, and get different answers. Now, I will tell you also, they are really kind of, I don't say obvious, but they're functions that don't look normal, meaning they're piecewise functions. So someone has to work hard to give you a function that's not going to meet this criteria. A normal-ish function, like if I just said do something x's and y's multiplied together that wasn't a piecewise function, you can generally expect this to equal that, which is good. We'll talk about when they're not equal another time, not before a test.
Confused on the difference between the fxx, fyy, and the fyx.
Sure.
So it's like we're doing like a double derivative.
Right, exactly.
So-
Let me answer your confusion with an example, because I think if we do more examples, it'll become less confusing. So, yeah, let's look at this example. This is a perfectly normal function of two variables. F of x comma y equal to x to the fourth plus y cubed plus x squared times y to the fifth. Just as a reminder, before we get going on this one, how constants work. So if my function were, say, tangent of x plus 3, the derivative would be secant squared of x plus 0. Because constants on their own, their derivative is just 0. On the other hand, if my function were 3 times tangent of x, then the derivative would be 3 times secant squared of x. Because constant multiples, I like to just say they hang out, right? Constant multiples stick around. They're the derivative of a multiple times a function is the multiple times the derivative of the function. So we're going to use that. Remember that when we start taking the derivative of this stuff. So let's find fx, the partial derivative with respect to x. So the derivative of x to the fourth is 4x cubed. The derivative of y cubed is 0, right? Because y is a constant as far as x is concerned. The derivative of x squared times y to the fifth is the derivative of x squared times a constant. So that constant multiple is going to hang out, and the derivative of x squared is 2x. Definitely interject if you have questions. And there's no real need to simplify this, but I suppose we could write it as 4x cubed plus 2xy to the fifth. We don't need the 0 there, really. Yeah. You would. So that's a good question. If we use the product rule for the partial derivative with respect to x of x squared times y to the fifth, we would get 2x times the not derivative of y to the fifth plus x squared times the derivative of y to the fifth, which is right. And so that part goes away. That's actually where the constant multiple rule comes from in general. It's really just the product rule boiled down to the second part's going to be 0, so we don't write it. Right? Same deal here. I could have taken the derivative of 3 tangent x using the product rule. It would have been 0 times tangent plus 3 times secant squared. Oh, that gives me 3 times secant squared. Same idea. Good question. All right, let's find the partial derivative with respect to y, which is del f del y. So now the derivative of x to the fourth is 0. And the derivative of y cubed is 3y squared. And the derivative of x squared, a constant, times y to the fifth is going to be the constant x squared times the derivative of y to the fifth, which is 5y to the fourth. And then I would simplify this as 3y squared plus 5x squared y to the fourth. It is fairly common practice to write things in alphabetical order, or as mathematicians like to say, lexicographic order, because why would you say alphabetical when you can make it sound more mathy? Lexicographic is just math speak for alphabetical order. Let's find the second derivatives. So fxx is just the second derivative with respect to x. So we're taking the derivative of the derivative with respect to x again. So basically you're taking your fx and just differentiating with respect to x one more time. You can write it like this if you want. It's del x of fx, which is the derivative with respect to x of our 4x cubed plus 2xy to the fifth. So we're going to get, well, the derivative of 4x cubed is 12x squared. And the derivative of 2x times a constant is 2 times that constant. Right? The derivative of 2x is definitely 2. So the derivative of 2x times a constant is definitely 2 times that constant. Constant multiples just hang out. Let's find fyy. So again, that's just the derivative. So it's just your partial with respect to y, taking the derivative of that with respect to y again. So it's going to be the partial derivative with respect to y of this 3y squared plus 5x squared y to the fourth. Derivative of 3y squared is 6y. The derivative of a constant times y to the fourth is my constant times 4y cubed, which I would simplify. I'm going to write that as 6y plus 20 x squared y cubed. All right, and then finally, for the mixed partials, we'll do it both ways, but I will tell you they're going to be the same. So for fxy, I don't know why I would use a different color there, I wouldn't. So for fxy, you're doing you're doing x first, then y. I don't have great notation for this, I guess. I know you're not going to love this, but it's del squared f del y del x, because you're doing x first, y second. On my pens, I need new pens. There's so much ink in there. I don't want to throw you away. It seems so wasteful. I know. It's not really that important. So del y of del f del x, which is right there. There's my del f del x, which is 4x cubed plus 2xy to the fifth. So I'm taking the derivative of this with respect to y. So the derivative of 4x cubed is 0. The derivative of 2x times y to the fifth, well, the 2x constant multiple hangs out, and the derivative of y to the fifth is 5y to the fourth. And then simplifying, we get 10xy to the fourth. And we would expect the derivative, the mixed partial in the other way, to be the same. So fyx, which is del squared f del x del y, or del x of del f del y, which is just del x of 3y squared plus 5x squared y to the fourth. The derivative of 3y squared is 0 with respect to x, and the derivative of 5x squared times the constant is 10x times the constant. And oh, look, those are exactly the same, which they normally are. So if I was doing this like as a student and not as a teacher, I would not be writing out quite so much, right? I wouldn't write out fyy as del y, right? I would be like I would actually do it more like the way I'm going to show you for this next example. So what's time? We got plenty of time. So let's look at another example. A quotient rule example. So f of xy is going to be x over x plus y, which it might or might not be convenient to think of as x times x plus y to the negative first. So let's find fx. I'm probably going to use the quotient rule. So it's going to be the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 1 plus 0 over the bottom squared, which is going to equal, if I simplify, x plus y minus x over x plus y squared, and the x's cancel on top, and you get y over x plus y squared, which I might want to think of as y times x plus y to the negative second. And to be honest, I typically find it, if I'm doing like all the first and second partials and the mixed partials, I think it's usually kind of easier to do fx and fxx right in a row. So I'm going to do fx and then I'm going to do fxx. So I'm just going to take that one there and take the derivative of that with respect to x. Okay, I can't help myself because I'm not a student, I'm a teacher, and I'm going to show you the things I think I should show you. So I'm taking the derivative with respect to x of this thing here, y times x plus y to the negative second. That's a constant. It's going to hang out. Watch this. That's a constant multiple. It's y times a function of x. It's going to hang out. So I'm gonna get y times the derivative of x plus y to the negative second, or the derivative of some stuff to the negative second power is -2 times my stuff to the negative third power times the derivative of my stuff. What's the derivative of my stuff? Yeah, 1 plus 0, 1. And then we can simplify this a little bit. I would probably write this as -2y over x plus y to the third. All right, let's find the partials with respect to y. So fy, taking the derivative of this with respect to y, it's going to be the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is 0 plus 1 over the bottom squared. That ends up being just a negative x over x plus y squared. Or if we prefer, a negative x times x plus y for negative second. Let's find fyy. Okay, so I'm just taking the derivative of this with respect to y. So it's going to be that negative x is going to hang out. And the derivative of x plus y to the negative second is -2 times x plus y to the negative third times the derivative of the insides, which is 0 plus 1. So that's going to end up being a positive 2x over x plus y to the third. Okay, let's find fxy. So for fxy, I'm taking my partial with respect to x and then differentiating that with respect to y. So I would probably encourage you to rewrite this as the partial with respect to y of my fx, which is the partial with respect to y of this mess here. So now I do have to use the product rule, right? So here, when I took the derivative with respect to x, I just had a constant times a function, and the constant just got to hang out. But now I have a variable times a function, and now I have to use the product rule. So my derivative is going to be 1 times the other piece plus y times the derivative of the other piece, which is -2 times x plus y to the negative third times 0 plus 1. And then, yeah, maybe I should have done this one with the quotient rule instead. But if we simplify this, I have 1 over x plus y squared. And then here I have a minus 2y over x plus y cubed. And if we multiply this first piece by x plus y over x plus y, you can simplify it and get x plus y minus 2y over x plus y cubed, or x minus y over x plus y cubed. And what I would encourage all of you to do on your own is show that this is the same as the mixed partials in the other direction. I think that'd be a good problem for you all to do on your own when you have a moment. It's not too terrible. It's virtually the same work, but just a little different. Let's see. I feel like there was something. Okay. Before I keep going in this vein, although we can certainly do more problems like this, I should ask, were there any questions from the practice midterm that you would like me to go over? Yeah.
There was one that you like heavily implied with the on meeting.
Okay. I do have the practice midterms here. You can tell me which one it is.
Problem 3, when you got to like part B of it, it's very, very, very good.
Problem 3B. Find the plane. Okay, yeah, we can definitely go over that one. Sure. Yeah, that's a good problem. Okay, so we can do more partial derivatives after we do a couple of these problems if we have time. But I feel like we've covered the basics of partial derivatives. It's not really any more complicated than what we've done, other than the functions might be more complicated. But the idea is very much, if you're differentiating with respect to x, pretend y is a constant. If you're differentiating with respect to y, pretend x is a constant. If there's more variables, like if you had a function of x, y, and z, and you differentiate with respect to x, pretend y and z are constants. That's really all there is to partial derivatives. At least that's all there is to executing them correctly. 5C, question 8. All right. Okay, so let's look at 3B. So find the plane in standard form determined by intersecting the line. So we are plane determined by the intersection of lines. We have L1 given by x equal to t, y equal to 3 minus 3t, z equal to -2 minus t, t between, yeah, I don't need to write that part. T can be anything, sure, yeah. And then L2 is x equal to 1 plus s, y equal to 4 plus s, z equal to s minus 1. So here's the thing, I was helping someone with this problem before, and here's the place where we kind of spent way too much time on this problem. You don't need to find where these planes intersect or where these lines intersect. I'm gonna say that again. You don't need to find where these lines intersect. To find the equation of a plane, so for the equation of a plane, you need two things. Thing one, you need a point in the plane. Well, both these lines are completely in the planes. So literally let t equal 0 or let s equal 0 or whatever you like and get a point. Thing two, you need what? What's the other thing that helps us determine the plane? You need a normal vector. That's all you need. So I'm going to find a point. Okay, great, point. I'll change it up just for the fun of it. Let's let s equal -1, and we're going to get the point x, y, z equal to 0, 3, -1 minus 1 is -2. Cool. To get a normal vector, you don't have to draw a picture, but it might help to draw a picture to see what's going on. So if I've got two lines, picture is easy here. So I've got two lines in the plane, say here's L1 and here's L2. They're not perpendicular necessarily to each other. They might look like I've drawn them that way. My angle is not perpendicular necessarily. Well, I certainly know the vectors for those lines, right? The L1 vector is 1, -3, -1. And the L2 vector is 1, the coefficient of s, 1, the coefficient of s, 1, the coefficient of s. So if I have two vectors in a plane, and I want a vector that is perpendicular to both of them, aka perpendicular to the plane, how do you find a vector perpendicular to two other vectors? Everyone should be yelling out the thing they don't want to hear. Yeah, the cross product. Right, so we're going to take the cross product of these two vectors. It doesn't matter which order you do it in. V1 cross V2, V2 cross V1, not going to matter at all. So let's do V1 cross V2. So we're going to get, let's see, I, J, K, and then we have 1, -3, -1, 1, 1, 1. So that's going to be I times, I really do, so I will say, I can't tell you how many times I've made errors doing this calculation, right? It's just easy to make a mistake. You miss a sign, you miss something. I really strongly recommend actually writing out the 2x2 matrices so you can do the determinants and just being extra careful because it's super duper easy to miss a minus sign. So I'm going to have -3, -1, 1, 1 minus j times the determinant of 1, -1, 1, 1 plus k times the determinant of 1, -3, 1, 1. Okay, so then we're going to get I times, in fact, I would even write this part out too, even though I don't really want to. -3 minus -1 minus j times 1 minus -1 plus k times 1 minus -3. At least if you make them, if you show more work and you make a mistake, I think you're more likely to get more partial credit. So it's not a bad idea in that way as well. So we're going to get, let's see, -3 plus 1 is -2i. 1 plus 1 is 2, so it's -2j. And then 1 plus 3 is 4k. And I think he wants you to write little arrows over your I, J, and K or something. Like I saw a note in the solutions that was like, I like this, but not this. So do what your teacher wants. It's not that terrible. And then finally, we take our vector. So this vector, the normal vector being -2, -2, 4, that gives us the coefficients of x, y, and z. So then we can say that our plane equation is -2x minus 2y plus 4z equal to a constant. Plug in your point. Where's my point? I forgot where it was. Somewhere I lost it. It's right there. Plug in your point. So 0 minus 2 times 3 plus 4 times -2 equals my constant. So my constant is going to equal, what is it, -6 minus 8, so -14. And then finally, simplify this and write it as -2x minus 2y plus 4z equal to -14. And technically, I think we should probably divide everything by 2 here, because we can. So or even by -2. So write it as x plus y minus 2z equal to 7. I know the question says find the plane in standard form. I forget what standard form is, to be honest. I feel like it's either ax plus by plus cz equals d, or ax plus by plus cz plus d equals 0. Either way, whereas the d, 1d is the opposite side of it. So either way should be fine. You might ask for clarification on that from your teacher. I don't actually know if like this would be considered not standard form since it's a multiple of that, but I wouldn't also worry too much about it. All right. I know you had a question. Which one did you want?
Oh, 9.
9. All right, let's see, look at 9. And then we'll look at the Zoom ones, 5C and number 8. But yeah, that is a good question. So the thing, again, I will emphasize there, we didn't need to find the point of intersection. Right? If we were told the lines intersected, they might ask you to find the point of intersection for a different problem, but we didn't actually need that point. All you need, so it's really important. Like if you're trying to find a thing, you should really think about, what do I need? For a plane, I need a point and a normal vector. It doesn't have to be the point where the 2 lines intersect. It can be any point. For a line, I need a point and a vector. So just think about what you're looking for before you start doing more work than you need to. It's always dangerous. Problem 9, cool, more partial derivatives. And we won't do 9b because he said there wasn't going to be limits, right? Yeah, so we won't do 9b, but we will do 9a. So, although 9b we could totally do if we really wanted to. So 9a, find the first partials of the following function, f of x, y, z equal to, oh, yep, thank you, of course. Thank you, yeah. The function is e to the xy, why would you write yxz? I would definitely write xyz just because, right? Why would you write letters in the out of order? Unless there's a really good reason to. Times sine of y. Oh, fun times indeed. I want to do that? Not really. So part of me kind of wants to simplify this before I start taking derivatives. You don't have to, but and in fact, I'm going to do it. Yeah, sorry, let me back up one second. Someone asked for the point, you simply pick a number within the range and plug it in. Yes, exactly. I picked s equal to -1, but you could have picked t, a more normal choice, no pun intended, right? Normal, okay. Would be to pick like t equal to 0 or s equal to 0. But any point is good as long as your t or s is in the domain. I will mention here that that actually is maybe not super helpful actually. I was going to factor out a z and write this as e to the z times x, y plus 1. But I don't know if I really like that. So you could do that, but let's just deal with this as is. So let's find fx. So for fx, what I am noticing is a constant sine of y times e to a function of x. And I know that the derivative of e to the stuff times the derivative of the stuff, right? It's just the good old chain rule once again. So for this function here, the derivative of e to a function times a constant, that constant's going to hang out. I might even write it in front, but I won't. So the derivative of e to the stuff is e to the same stuff times the derivative of that stuff. Okay, the derivative of that stuff with respect to x. So can someone tell me what the derivative of xyz is? YZ. Can someone tell me what the derivative of z is? Yeah. And then I'm going to multiply by sine of y because it's a constant multiple and it just hangs out. I would probably rewrite this, not that you really need to, as e to the xyz plus z times yz times sine of y. Or just not write the 0 in the first place. All right, let's find fy. Fy is a little worse because now I have a function of y times a function of y. So I'm going to think of, for this problem, I'm going to think of this as my f and this as my g. And I know I'm going to need an f prime times a g plus an f times a g prime. All right, product rule. I'm setting expectations here. So the derivative of this part is going to be virtually the same as it was before. The derivative of e to the stuff is e to the stuff times the derivative of that stuff. But now the derivative of xyz is xz, because we differentiate with respect to y, plus 0, which I'm not going to write this time. And then it's going to be, that's it. And then we have to multiply by, now so I've spaced this out kind of weird because I got too excited about the problem, times sine of y. Plus, then we flip it. We leave the f alone, xyz plus z, and then it's going to be multiplied by the derivative of g, which is cosine of y. Part of me really was struggling not to like write a y prime at the end. Right? It's not implicit differentiation. You don't do the derivative with y and you throw in a y prime. None of that. But it felt like I wanted to.
Where'd the plus come from?
Product rule. Yeah, product rule. Sorry. Yeah. So, right, when you take the derivative of a function times another function, not times a constant, but times a function, you do the derivative of the first function times the second function plus the first function times the derivative of the second function. That's where the plus is coming from. Let's look at the third one, the last one, the partial derivative with respect to z. So again, well, actually back to like my first iteration here. Now I just have a function times a constant, and that constant multiple is going to hang out. So the derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff. But now the derivative of xyz plus z is xy plus 1 times sine of y. So that's how you do that one. We can definitely do another one. Like we might, if we have time after we do problem 5C and 8, we can do more partial derivatives. Let's look at 5C. Okay, yes, it's not too terrible. A particle's position is defined by r of t equal to 2 cosine of t in the I direction plus 3 sine of t in the j direction plus 4t in the k direction. Find the particle's speed and direction of motion at t equal to pi. So to find speed, speed is the magnitude of velocity. So to find the speed at t equal to pi, we first need to find the velocity at pi and then take the magnitude of it. So let's find the velocity vector. That's just found by taking the derivative. So the velocity vector of the derivative 2 cosine t is -2 sine of t. It's an I, not a j. The derivative of 3 sine of t is 3 cosine of t, j. And the derivative of 4t is 4. Okay. So there's your velocity at any time. Here's our velocity at pi. It's going to be -2 sine of pi I plus 3 cosine of pi j plus 4k, that is a 4. Sine of pi is 0, so I'm going to get 0I. Cosine of pi is -1, so minus 3j plus 4k. So there's my velocity vector at pi. And then the magnitude of that vector is just the square root of 0 squared plus -3 squared plus 4 squared, which is going to be 5. So I would write some words, right? I would say the particle speed at t equal to pi is 5. And I wouldn't even deign to put any units because there aren't any units given in this problem, right? So if they say it's moving like, so many feet per unit of time, then you should put units, but usually units are not really a big part of what we're doing here. For the direction, right, because it says find the particle speed and direction, direction should be kind of just an easy consequence of what we've already done. So if you know the velocity vector and you know the magnitude of that vector, you know the direction. The direction is literally just the vector you had divided by the magnitude of the vector, right? Because whenever you're talking about a direction vector, if you hear the word direction, in goes direction, out goes unit vector, right? If you hear the word direction, you should automatically think, oh, I need a unit vector, because the person grading this wants all the same answer from everyone, not 20 different answers of vectors of different lengths. So our direction is going to be our vector divided by its own magnitude. At least I think that's what he wants. Let me look at the answers. Maybe he's looking for something totally different. I feel like I'm not wrong, but I should check just to be sure. You gave 2? Interesting.
Said one was the direction of motion and one was the direction.
Oh, right, because time is moving forward. Sure, that's fair. Well, he's written that up. Interesting. Oh, and also an equation of the tangent line. Sure. Yeah, okay, interesting. So he does not seem to particularly care. Oh no, he has given it. Okay. So he said that one was the direction of motion and one was just the direction. Interesting. So typically when people ask for direction, they usually mean they want to have a unit vector. He has definitely said a couple different things here. I would default to the safe side of things and find the unit vector. So it's going to be my vector 0I minus 3j plus 4k all divided by 5, or if you prefer, -3/5 j plus 4/5 k. Right, the 0I you don't need to write. Yeah. He's got a little, yeah, I'm curious about the little star here because he's definitely a direction of motion and then direction. I feel like either answer is probably fair enough. Because the thing is, like, if I was talking about the direction of a vector, I'd be like, well, it points that way. I don't care if you tell me it's pointing that way really long or really short. And apparently he doesn't seem to care either. So you might be safe either way. I would still default to normalizing that vector. As far as the equation of the tangent line at that point, so to find the equation of a line, we don't particularly care that it's tangent. We need a point and a direction. So I'm going to take, now this is where I actually would use the not normalized direction vector. So my point is the point at time equals pi. So my point is r of pi, which if I plug in pi, I know you guys can see this thing. If I plug in pi to my original equation, I'm going to get 2 times cosine of pi, which is -2i, 3 times sine of pi, which is 0j, and 4 times pi. Okay. So that's the vector, but the point I actually want is the point -2, 0, 4 pi. And then the direction vector, we've already found it. It's the velocity vector. but I am going to write it as the not fractional one because I think it's nicer. So I'm going to use that vector right there. Sorry, things get a lot of control there. So my direction is going to be the vector 0, -3, 4. And then if you're finding the equation of a line, it's always your initial point or whatever point you've got plus t times your direction vector. And I do like the way he's written it here. I would write that my tangent line is given by the equation, the point I want to start at plus t times the direction I'm going in. And then you should say that t can be any real number, or it's between negative infinity and infinity, whatever you would say. It would also be perfectly correct to use the vector 0, -3/5, +4/5 there. That would also give you the exact same answer. Yeah. Because he asked it for it. But right, that no other good reason other than it's part of the question. Yeah. And we had number 8. Oh, yeah, good. Yeah, fair enough. Back to what we were. So number 8, we've kind of already talked about, but I think it's worthwhile still. So let's go back to number 8. So consider the function. What time it is? Oh, yeah, we got time. Z equal to 4 minus, oh, he was nice. He even wrote it as x squared plus y squared. How convenient. Oops. It'd be convenient if you could see it. So I know I'm like some people, I watch other people's videos and like things always in frame. I'm like, wow, how do you do that? Like clearly beyond me. So first domain. No issues, right? No roots, no logarithms, no fractions, no inverse trig functions, right? Inverse trig functions are also weird functions that have limited domains, but okay. So the domain is all of R2, or whatever way you prefer to write that. Just make sure you don't say all real numbers, right? It's not all real numbers, it's all real coordinate pairs. Find the range. So again, if I'm looking at something like this, I'm always remembering that x squared plus y squared has to be greater than or equal to 0. So that means the smallest this can be is 0, which means the biggest this whole thing can be is 4 minus 0. Because to make this as big as possible, I have to make the thing I'm subtracting as small as possible. So we definitely for sure know that the biggest this can be is 4. There's no way it can be larger than 4. If you're not sure, set it equal to 5 and try and solve. It's not going to work. If I said, in fact, right, I set this equal to 5. And then I subtract 4. And then I multiply both sides by -1. Oh, that's going to be a problem. That's not going to work. X squared plus y squared can't equal -1. So we definitely can't get to 5 or anything beyond 4, really. And then this can certainly be as negative as you want it to be. Just let x be larger and larger and larger, or y be larger and larger and larger. So our range here, and again, I know this is somewhat unsatisfying, but the range, there isn't really like one tried and true method of figuring it out. It's just kind of like, ask yourself, how is it going to be big? Ask yourself, how is it going to be small?
Yeah, let's do the rest of it.
Okay, sure. Okay, yeah, if you were graphing it, certainly, yes, you would also, that's a fair point. Yeah, and then we want to do the traces. Okay, so we're going to sketch the, I guess the XZ and the YZ traces. Yeah, that's what you would usually trace. So the XZ trace. So when you're finding a trace, all you're doing is you're setting the variable that's not mentioned equal to 0. So the XZ trace, y equals 0. So you're going to get z equal to 4 minus x squared. Well, great. I can draw that. It's just a downward opening parabola. And the intercepts are 2 and -2. And then for the YZ trace, same deal. X equals 0. You're going to get z equal to 4 minus y squared. It's going to look literally the same. I feel kind of silly drawing it. That's why, let's see. Sketch and label at least 3 level curves. Okay, so to do this the most efficient way we can, we're going to set our function equal to a constant. Now, you should take note, if you've already found the range, we know that that constant can't be a value outside of the range. So then I'm going to isolate the x squared plus y squared. So I'm going to have 4 minus c equal to x squared plus y squared. So I know that this is going to be a circle centered at the origin, and the radius is going to be what? Square root of 4 minus c. So then I can pick c values and draw things pretty easily. Like, and I'm probably going to pick like convenient c values. Now I'm going to pick c equal to 3 because that's going to give me the square root of 1. And I'm going to pick c equal to 0 because that's going to give me the square root of 4. I'm going to pick c equal to -5. Why not? Because that's going to give me the square root of 9. So if c equals 3, I get a circle of radius 1. And you should label how high you are, because that's what c is. It's how high you are. And then c equals 0, I'm going to get a circle of radius 2. And then c equals -5, I'm going to circle of radius 3. So we can see that the lower we go, the wider, the bigger the circles get. And then finally, sketch it. We've sketched something like this before, but I can sketch it again. But basically, the idea is that these are supposed to give you like a good idea of what it looks like, right? We know that our trace in the YZ plane looks like this. And then our trace in the XZ plane looks like that. And then it's kind of like that. Downward opening paraboloid. My picture's not the best, but you know, that'll be forgiven. All right, 3:02, I should stop talking.